Let's try some practice problems. Let's be sure to try these on our own first and then compare with me. Just an overview, we see these are all alkenes. They're going to be treated with a bunch of different conditions. So for everyone, I want to think about what atoms are adding. We also want to think about regiochemistry, so which atom of the alkene adds to which atom doing the addition. And because these are asymmetric alkenes, meaning that the two carbons of the alkene are different. Okay, so give this a try. Seriously. Great, so I have the broad strokes of the answers here, and we're going to go ahead and go through them one at a time. So for HBr addition to an alkyne, we or an alkene, we had H and Br. We will have hydrogen adding to the less substituted of those two carbons of the alkene, and bromine adding to the more substituted. This is because of the mechanism of the reaction, and because we will observe the most stable carbocation. So in the first step, protonation occurs. Protonation occurs to carbon 1 to generate the tertiary cation, which is trapped in a coordination step by bromide to generate the product. So I have written out H and Br here, but you're going to see the product drawn like this, where that hydrogen is implied. Cool. Next example, we have acid catalyzed hydration. So we're going to be adding HOH across the two carbons of the alkene. We want to look out for rearrangement, but this reaction will involve the same cation, and it's not prone to rearranging. So we will get the tertiary alcohol, where the more substituted carbon of the alkene did bond to oxygen. Next, we have halogenation with bromine. And now this reaction does not go through cations. It goes via a bromonium ion. So we have pi Cc attacking sigma star BrBr, and then the non-bonding orbital on bromine attacks back. That generates the bromonium ion. The two bonds to bromine should be on the same face, and they can be the top face or the bottom face, just depending on which face of the alkene reacts, which side bromine bumps into, and both of those possibilities are equally likely, which is why the product is racemic. So then from there we will have the nucleophilic electron-rich bromide opening up the ring, because bromide is a weak nucleophile, and this is a really this is a positively charged electron poor species. We remember that the more substituted carbon shares the charge, and bromide is just attracted to that as it floats by. Really key to remember that we have this anti-addition of the bromines because of this key step with the bromonium ion. Now, the next reaction, really similar reaction. This is halogenation, but in the presence of an alcohol, and so it will form this vicinal halo ether. Whereas in the previous example, we observed a vicinal dihalide. But in the presence of an alcohol or water, instead of bromide opening up the bromonium ion, we could see methanol, or whatever the oxygen-based nucleophile is, open up that bromonium ion. Again, this reaction is really similar to if we'd had a protonated epoxide. We'd had the analogous protonated epoxide. We would expect a neutral nucleophile like methanol to attack the more substituted carbon to which, in an SN2 fashion with inversion of stereochemistry, but it's that weird SN2. So that's what we see here. Weird because we see the more substituted carbon attacked. And we see this anti-relationship between the bromine and the ether functionality because of the mechanism, because of that bromonium intermediate. And then again, racemic because either bromonium ion can be made. Finally, our last example, let's try to zoom in a little bit. This is a hydroboration reaction. And what's special about it is that it's a hydration and you have anti-Markovnikov selectivity and a syn addition of H and OH across the two carbons of the alkene. So anti-Markovnikov, this time we have the less substituted alcohol versus with acid catalyzed hydration, we had the more substituted. So we had the tertiary. For acid catalyzed hydration, we have the secondary alcohol for hydroboration. It is important to keep in mind that we just have the syn addition of HOH. So you will have a racemic mixture of this product here because borane can add to either side of the alkene, but you have one diastereomer. And don't be confused. Usually, we don't show the hydrogen. So if you look over at where I've written it out with the implied hydrogen, the hydroxyl and the methyl, they're anti, but that's because hydroxyl and hydrogen are syn. It's hydroxyl and hydrogen that add syn to one another. For these problems, we really focused on regiochemistry. So which carbon of the alkene was making bond to which of the two atoms adding across the alkene. But for the next set of problems, we're going to look at the symmetrical alkene, and we're going to focus more on the stereochemistry of the products. So please go ahead and try these problems. It's really important to try them yourself so you get the most out of it, and then we will look at them together. All right, I have the broad strokes again of the answers, and then we will go through them now together. If you would like to go through them on your own first, that is totally cool. So for hydrohalogenation reactions where we're adding HX across the two carbons of the alkene, this reaction goes by carbocations. And in the first step, there can be protonation to either face of the alkene. So that means that you'll get protonation to the bottom face and protonation to the top face. And the relationship between these two cations is that they're enantiomeric. So these are enantiomers where the stereocenter is right here. And then now to these flat carbocations, we again can have addition to either the top face or the bottom face of the carbocation. So either face again. So for each of these two carbocations, we can have addition to either face, and that ends up giving us a racemic mixture of diastereomers. So basically, HX addition is just a mess. There's no stereoselectivity for this reaction. Bummer. There might be a little bit of stereoselectivity, but it's definitely not stereospecific, and it's not useful stereoselectivity. So let's just say not stereoselective. And you can get into all the tiny details if you ever take advanced organic chemistry. Not really stereoselective. Great. Now, the next reaction, the first step is stereoselective. Unfortunately, the second step scrambles everything. So in the first step, we added mercury to either face of the alkene. Okay, so you can have this, and you can have mercury on the bottom face. And for this is so fun, let's just draw it out. Why not, right? All right, methyl's up, mercury is down. Oh, yeah, okay. All right, so we can have mercury on either face. And then when water comes to open this up, water does so from behind the carbon-mercury bond just because this is an SN2 reaction, right? It's a weird SN2 because it would attack the more substituted carbon if the alkenes were asymmetric, but they're not. And it can attack either carbon, which is why you'll see racemic mixtures of the product. So the first step is stereoselective. We would have a racemic mixture after deprotonation of this anti-isomer. But then step 2, where mercury is replaced by hydride, step 2 is not stereoselective, meaning that even though the carbon-mercury bond is up in the isomer that I drew, the carbon-hydrogen bond is going to be up and down. Bummer. So you can have the carbon-hydrogen bond stayed up, or the carbon-hydrogen bond can end up being down and the methyl can be up. So those are diastereomers of one another, and they started out racemic. So you have a racemic mixture of diastereomers. Again, a mess. So for both of these first 2 reactions, we have a racemic mixture of diastereomers. So also here. Now, thankfully, luckily, these next 3 reactions actually have some stereoselectivity and stereospecificity. So that'll be nice for us. I'm going to make some room so we can take a look. Cool. So let's look at formation of the chloronium ion. So this reaction to form the vicinal halohydrin occurs via a chloronium ion. So the alkene attacks chlorine, chlorine attacks back. This, of course, can happen to either face of the double bond, but both faces are exactly the same, so you can't tell the difference. Okay, but we have this chloronium ion. It can add to either face, and that definitely happens, but we can't tell the difference because this is symmetrical, so I'm not going to bother this time drawing out addition to both faces. And then you can have water attack either carbon of the chloronium. So either carbon is attacked, and either carbon being attacked leads to the racemic mixture of products. But, so either carbon is attacked, but it has to be to the opposite face. And because it has to be to the opposite face, because this is an SN2, and that is where the carbon chlorine sigma star is, we only see the anti after deprotonation, we only see the anti-diastereomer, but we will have both enantiomers. So you would have the enantiomer that I drew here in orange and the enantiomer that I drew in blue. Those are the 2 enantiomers of the anti-diastereomer. So there's only one diastereomer for halohydrin formation, and it's because of this awesome chloronium intermediate. And again, water has to attack opposite to sigma star, because that's where it is, opposite to the carbon chlorine bond, because that's where sigma star is. Cool. Next example, epoxidation. Well, we know that both bonds to oxygen are formed at the same time, so they have to be formed at the same face. Okay. And then I think I explained hydroboration to you on the previous slide. Did I draw it out? No. Okay, well, let's draw it out now. I probably did, but it's just so fun. Let's do it anyway. All right, so when the boron and hydrogen bonds form, they do form to the same face. And like I said, this time the second step is stereospecific or stereoselective. And so stereochemistry is retained. So that hydrogen is going to stay down here on the bottom face. And if it had, so I should attack to the top face here. It could have been to top or bottom face. But no matter what, you have the hydrogen and the hydroxyl ending up syn. So you have the syn diastereomer, just like we saw anti-diastereomer for halohydrogen formation. We have the syn diastereomer, but we have a racemic mixture because the initial attack, this attack, could happen to the top face like I showed, or it could happen to the bottom face. Excellent work. We have discussed stereochemistry, regiochemistry. Now let's think about when carbocation rearrangement happens. So take a little pause, try these questions on your own, and then let's discuss them. Last chance to pause. Excellent. Again, I have the broad strokes here. In the first reaction, we have oxymercuration. Oxymercuration does give the most substituted alcohol made from the 2 carbons of the alkene without rearrangement. So we have the secondary alcohol, no rearrangement. This is because there are no cations. This reaction goes through this mercurinium ion, which reminds us so much of a protonated epoxide or a bromonium ion. And in this, there's a little bit of charge share, with the more substituted carbon because it can, right? More stable carbon or more substituted carbon can stabilize a little bit of partial positive by hyperconjugation with its substituents. Cool. So then water attacks the more substituted carbon and you end up after step 2 with the OH bond there. No rearrangement for oxymercuration reduction. Excellent. Next example, there's hydroboration oxidation. What do you think? Well, we get the anti-Markovnikov product. There are no cations. So guess what? No rearrangement. Good. Now we move on to acid catalyzed hydration. Are there carbocations in this reaction? 100% there are. So the first step is protonating the alkene. That generates this secondary cation that is bummer adjacent to a strained ring. The ring opening breaks that strain. Then you'd end up with this cation, which if it were to get trapped, would generate this product as a mixture of diastereomers. Again, bummer. Or it could keep rearranging. Oh my goodness gracious. You could keep rearranging. Hydride could shift to make a tertiary cation, so this hydride could shift. And then if that happens and this gets trapped by water, then you get the other constitutional isomer that I have drawn here. And again, this would be a racemic mixture of diastereomers. And then the other, its constitutional isomer is achiral. All right, what a mess. Acid catalyzed hydration. Definitely cations, definitely rearrangement. Bummer. Next one, what's going on there? Okay, so for halohydrogen formation, this is another example of a reaction that goes by cyclic intermediate, cyclic transition states. And guess what? There's no cation. Now, the regioselectivity is determined by carbocation stability, but it's just because this carbon just shares a little bit of a charge, just a little bit. And so water comes and attacks it, but there are no full cations. So there is no rearrangement for that one. All right, awesome. Last one, we have HBr addition. Same explanation as for acid catalyzed hydration. There's the same cation that's formed. This one, it ring opens, it can keep going, and that can make the 2 products shown. Okay, we're going to take a look now. These are typically harder questions, so the predict the reactant questions. So go ahead and take a look at these and then come back. So we're treating with 9-BBN and really making an aldehyde, and you really just don't have but one option here, which is that these 2 carbons were the two carbons of an alkyne. And I'm not sure why I'm solving this problem here because I'm pretty sure I've already solved it on the next page. Yeah. Okay, so those two carbons of an alkyne. All right. We'll point out here, I put these benzene rings on purpose. They just don't react under any of the conditions that we've learned so far. So if you see a benzene ring, it doesn't react. Don't make it do anything until you hear from me, until you get further notice, but it won't be this semester, so don't react benzene rings. All right, for the next example, we have chlorine adding, and you know that chlorine adds in an anti-fashion when it adds. Okay, but this is an acyclic product, so there certainly is free rotation around this bond. Now, when you see that these two chlorines are syn, that just means that this conformation of the alkyl chain, that is not the conformation that it was in when chlorine added. Okay, so in other words, when chlorine added, those phenyl groups were syn to one another. So as soon as when chlorine first added, look like this, okay? And then there is free rotation to get there. Because, you know, having the phenyl groups anti to one another, having the alkyl chains anti is definitely the most stable conformation of the alkyl chain. But when chlorine added, it added in an anti-fashion, and this came from the cis alkene. So you just want to be careful here. And then now, like the rest, this was tricky, and like for the rest of these, I made them tricky too. It's not always tricky. I don't know. I wanted you to see some tricky examples, but I'm telling you, it will not always be tricky. So for example, if the problem with chlorine looks like this, where the chlorine groups are, I lost my words, I'm sorry, where they're anti to one another, then it's really straightforward. You just draw the alkane like that because they add an anti. They're anti right now, so this is the conformation of the alkyl chain when they added. So for the next example, we have hydroboration. And for certain, this carbon bonded to oxygen was one of the carbons in the alkene that made this product. Okay, so it's that carbon right there. But you really have two choices. The alkene can be here or the alkene can be here. If you had the terminal alkene, you would not get this product from hydroboration because this carbon is less substituted. So if you had an alkene here, if you had this alkene and you hydroborated it, the primary would get oxygen, the secondary would get hydrogen. So you wouldn't get this. So you know that that's not going to be right. So you have the alkene between carbons 2 and 3. Now the hard part is, well, now that we've figured that out, the next hard part is where is it going to be? What is the geometry? Is it E or Z of the alkene? So remember, for hydroboration, HOH are added syn. Now, in this conformation, H is anti to OH. So all that means is that this is not the conformation of the chain in the alkene. So that's no problem. I went ahead and I rotated around the chain. So I made these cis to each other, not trans to each other, because I can tell they're not trans because it doesn't have the right stereochemistry if they are. Okay, great. And just to be, I'm almost gonna be 100% sure you guys got it. So then if this alkene is treated under hydroboration conditions, you would have your hydrogen up, your hydroxyl up, push this methyl down, okay? And then you'd rotate around this bond, and that would give you your carbon chain in the all zigzag conformation as shown. Okay, last one. So you can see that an epoxide is formed from step 1, epoxidation. And then in step 2, it's being opened under basic conditions. The basic conditions. All right, so let's see. We know the epoxide has 2 methyl groups, and this is an SN2 reaction to open it up. So these groups are anti to each other right when the methoxide adds. Okay, but in the product, they're not anti, right? They're syn. So again, that means the methyl groups are not trans to each other. They should be cis to each other in the epoxide when it gets opened. So if you rotate around that bond, to make the methyls cis to one another, then these two groups would be anti. And we know, okay, well, when the nucleophile first adds, they should be anti, but this is a single bond, so free rotation is allowed, and then, you can draw your carbon chain in that full zigzag, which is what's going on here. But since this is the conformation in which the two groups are anti, that means that we should have our methyl groups send to each other in the epoxide, which means we should have the cis alkene. I told you these are tricky. Okay, good. Good. Propose a synthesis. I am going to roll through these. Pause if you want, and then I'm going to explain them. Vicinal halohydrin. This comes from an alkene, right? We treat the alkene with bromine in the presence of water. Make sure everything makes sense with the selectivity. Yes, the oxygen should add to the more substituted carbon. Bromine will add to the less substituted carbon, as we have discussed. 1, 2, 3, 1, 2, 3. And then somehow this alkene needs to come from this alkyl halide. Well, yeah, guys, we know how to do that. I know it's not this unit, so it might have left our brains, but it's just an elimination reaction. So we can do an E2. We'll use sodium T-butoxide and the alcohol solvent. There we go. So step 1, sodium T-butoxide. Step 2, halohydrin formation. Next example, and we're starting with an epoxide and generating. Whoa, what are we generating here? Well, this interesting ketone. Let's see if we can figure out what bonds were made. So it looks like this bond was made here because these two carbons are the carbon of the epoxide. Then we can think, what do we make ketones from? So you noticed I went back and I wrote down some functional groups. You should be labeling every functional group, particularly on synthesis problems. So what do we make ketones from? We make them from alkynes. So that would have come from this. Okay. Does that make sense? Yeah. So cool. Then that means from the epoxide to here, we have to make that bond as indicated. Can we do that? Yes, we can. We can open up epoxides with acetylide ions. We talked about that a couple lessons ago. So this undergoes an SN2 reaction, opens up that epoxide. You do need the proton source, so you can do a workup. You can treat with water afterwards. Okay, this proton has to come from somewhere, so it comes from the workup. And then to get to the ketone from the terminal alkyne, you know that it's an oxymercuration reaction. This is an example. Like if you hit this with sulfuric acid, this is going to do all kinds of undesired reactions. We're going to really carefully treat this with oxymercuration conditions, which are a little bit more mild. And that gives us our alkyne, transforms it into a ketone. Okay. Good. Well, I hope you found those practice problems useful. Hopefully they started out a little straightforward and got a little more difficult. And now it's just time for you to go do some more practice.